In this installment, we're going to take a look at torque and rotational equilibrium. And again, if we are going to make a comparison to our translational world, we would call that force and translational equilibrium. So net forces mean that there is not a translational equilibrium, there's disequilibrium. Balanced, a zero net force means there is translational equilibrium. In the same sense, a net torque means it is not in rotational equilibrium, is experiencing rotational acceleration. So let's situate ourselves in the course. In this unit, we've spoken about the moments of inertia, momentum and rotational momentum, change in momentum and change in rotational momentum, rotational kinetic energies. In our previous installment, we spoke about Newton's second law of rotation and compared it to Newton's second law of linear motion. And we're going to begin here by looking a little bit more closely at torque. Now, we'll start in this installment looking at torque as R times F. Now, some of you might notice right off the bat that we have V is R omega and alpha is R alpha. A is R alpha, and here we have this T equals RF. So the torque, tau, is RF. Now, I'll just point out here that the rotational cross over like this, and the linear behave like this. So whereas V equals R omega and A equals R alpha, F equals tau over R. And so we can think of this as being a conversion like the others, it just has a little bit different relationship, okay? But what this says is R, the radius, times the force perpendicular, the perpendicular force, is the torque. Okay, so that's the first thing. The second thing, we'll point out another summary here of F net is MA, which is the sum of the forces. And over here we have torque net, sum of the torques, I alpha. So our larger statements. So T equals RF. Now, let's just, one other thing that we want to point out here is our friend, the unit circle. And the unit circle, of course, we have quadrants 1, 2, 3, and 4. But this is about determining directionality. So directionality in this case, if we have a translational world, a dimensional, we say this is the positive direction and that's the negative direction, with this being 0. Well, here we have 0. And this is the positive omega, and this would be negative omega. Anything traveling in this direction is negative angular velocity, and anything traveling in this direction is positive angular velocity. So something traveling in this direction is positive velocity, something traveling in that direction is negative velocity. That's all we're doing is specifying that. Now, if there's an acceleration that's in the direction to the right, we say that's a positive acceleration, and if there is an acceleration that's getting faster in that direction, that's caused because there's a force in that direction, or in the case of the positive, a force in that direction. Well, just as there's an omega in this direction, if there is an alpha in that direction, then that must mean there's a torque in that direction. And if there is an alpha in this direction, that must mean there is a torque in that direction, a negative torque, negative alpha. So let's use that in a simple example here. I'm going to just demonstrate how we would compute torque, and we're going to pause this video and look at some of these as an animation. So let's see what we have depicted here. We have a fulcrum on a seesaw. When I was a kid, we called them a teeter-totter, but all of you in the modern age call them a seesaw. And of course, we know that it is free to rotate right here. What we have depicted is a fire extinguisher that has a mass of 5 kilograms. Therefore, its weight is 50 newtons, as is this one over here. We notice that the the fire extinguisher is on a board and there are distances indicated like so. And let's say we could call these, we can call them anything we want. We could call them decimeters or meters. The units aren't so critical for us right now. But if we were to look at the force, in this case, is in this direction, which is perpendicular to the radius. And the force in this direction is perpendicular like so. And so that's what we mean by a force perpendicular. It's got to be perpendicular to the direction or tangent to the circle. Okay, it's that part of the force is tangent to the circle. And so if we use our R perpendicular to F, in this case we have a radius of 8 and a force of 50, so we have 400 is the torque. Now the torque in this direction we said is negative. It's a negative torque. So we then say that the torque is minus 400. On the left-hand side, well, then our torque is RF, and we have 8 times 50 again, and that is 400. Positive 400 because this is the positive direction. Now the net torques are the sum of the torques, and that's minus 400 plus 400 equals 0. And if that net torque is I alpha, we know there must be a moment of inertia, so the alpha is 0. There will not be any acceleration here. Now, that's not a surprise, but this is how we do the accounting of it in physics. And of course, when you look at this seesaw, none of you was surprised to see that this seesaw was balanced.